In our last mini lecture, we talked about granitic magma being highly viscous or resistant to flow. So the word viscous is related to the concept of viscosity. And again, viscosity is really just resistance to flow. We're going to look at two very different volcanic eruptions and talk about the viscosity of each. So let's start here in Hawaii. And I would just like to say that I do not recommend what you're going to see in this video, but it is pretty cool.
Daredevil professional kayakers Pedro Oliva, Ben Stooksbury and Chris Korbulik headed to Hawaii to paddle amongst molten lava flows. They came across this amazing scene during their search to find and paddle in the world's most extreme places.
A nossa expedição tinha como objetivo encontrar rios e cachoeiras no Havaí. E a possibilidade de ver um rio de lava realmente foi o que nos atraiu.
The three professional kayakers were in Hawaii to film their TV program Kayak, an adventure kayaking series that airs on channel Canal Off. The fearless trio couldn't wait to get into the water for their challenge and paddled within meters of these lava flows on Big Island.
Eu e meus amigos Ben Stokesbury e Chris Kerbulik empunhamos nossos caiaques para chegar no rio de lava do vulcão Kilauea. O vulcão Kilauea está em atividade desde 1983 e é um dos vulcões mais ativos do planeta.
This whole island has grown by like a square mile in the last 10 years. This thing is literally the most recent piece of newly formed earth that you could possibly stand on, and we're seeing firsthand exactly what's making this beautiful island.
A sensação de chegar na
Okay, so that is one example of a lava flow. And again, that was in Hawaii. And here is a lava flow in Papua New Guinea.
Watch out for the shock, it's coming. Holy smoking Toledos.
So obviously a very different eruption, yes. So the nature of the eruption was because of the viscosity of the magma underlying each of those volcanoes. So what controls viscosity? If you think about it, and again, viscosity being the measure of the fluid's resistance to flow, there are a few things that might make some sense. If you think about liquids that flow, water, for example, has a very different resistance to flow than like molasses or maple syrup or agave. So let's think about what those parameters might be. The viscosity of a magma will determine the explosivity of an eruption. So the higher the viscosity, the higher the resistance to flow, the more likely a volcano is to explode as opposed to have sort of gentle lava flows. So there are three parameters that most directly control the viscosity of a magma. The most important, arguably, is the temperature of that magma. The hotter the magma, the easier it flows. You can think about this in terms of candle wax. When the wax is really close to the flame, it's very warm and it flows easily down a candle. And as that wax starts to cool, it starts to become clumpier and slow down, and it flows less. So magma actually behaves the same way, same thing when it's at the surface as lava. As you saw in your homework assignment, the amount of silica also greatly controls how easily a magma will flow. The higher the silica content in general, the stickier the magma, or the higher the viscosity of the magma, like granitic or felsic magma. The opposite is also true. The lower the silica content in the magma, like in ultramafic and mafic magma, the lower its resistance to flow, or the lower its viscosity. And then the last thing that you might have sort of picked up during our lecture so far is that the gas content, or the volatiles, also greatly control the viscosity rather of the magma. So gas content basically pressurizes magma chambers. So the higher the gas content, the more explosive the eruption in general. So if you recall, one of our low viscosity magmas that is very common on the Earth's surface is basaltic or mafic magma, which is a primary component of shield volcanoes, which we looked at earlier when you looked at Fernandina in the Galapagos Islands. Shield volcanoes are composed basically of a series of basaltic lava flows and have a summit caldera that is any summit of a volcano that is larger than 1 kilometer in diameter is considered to be a caldera. So anything smaller than 1 kilometer in diameter, which is a really random number, I'm not gonna lie to you about that. It was sort of arbitrarily picked, but anything smaller at the summit of a volcano is just referred to as a crater. So this is a picture of Mount Kilauea, which is the active volcano on the big island of Hawaii. It has erupted every day since 1983, which is very reliable. And you can see here from the black basalt that is cooling from this lava that these are just a series of basaltic lava flows. Mount Kilauea is a very famous shield volcano. So even within these really low viscosity lavas, there is some variability. So here's a picture of a basaltic lava flow. This is not from Hawaii. This is actually from Idaho. Idaho is a place I never thought I would go when I was a young lady, and have been to several times now, and every time am surprised by the volume of cooled lava flows that are in Idaho. This one is about 2,000 years old, but there are basaltic lava flows that cover Idaho much more than I ever thought they would. I just kind of imagined a field of potatoes, which just goes to show you that marketing matters, I guess. So you can see that this basaltic lava flow has weathered a little bit. Sorry to get off topic there. You can see this rust-colored sort of weathering surface on this basaltic lava flow, but you also probably notice how fluid it looks. Like you can tell which direction this lava flow is moving in. And this type of a lava flow, it's still basaltic, but it's referred to as a Pahoehoe flow. You should say that word out loud because it's a fun word to say. Pahoehoe is a Hawaiian word that I'm pretty sure means something like I can paddle a canoe through this, because it kind of looks like you could, right? It looks pretty fluid. A Pahoehoe flow is a ropey, very low viscosity lava flow. This is a basaltic flow so Pahoehoe is just sort of an adjective that describes this type of basaltic lava flow. Here's another example of a Pahoehoe flow. You can see that this Pahoehoe flow kind of flowed over a pre-existing flow, but again, you can see sort of just some of the fluid motion here. This one looks different. So these are some cinder cone volcanoes in the background here. But what you look at the basaltic lava flow, when you look at the basaltic lava flow in the foreground, it doesn't look like Pahoehoe flow, right? It looks a lot blockier, a lot more jagged. And that is because it is not a Pahoehoe flow. This is in fact called an Aa flow. An Aa flow is composed of very jagged rock. And the story is that the Hawaiians gave Aa flows this name because as you walk over it, it hurts, and in your bare feet you would say ah. I don't know if that's true, but it does help generations of geology students to remember it. So there you go. So this is still a relatively low viscosity lava flow. It's still basaltic, but you can tell that this is a higher viscosity than the Pahoehoe flow, right? Like this does not look nearly as fluid. This looks a bit more resistant to flow, and it is. It is. So here you can see an Aa flow in most of the photo, but here you can see that a Pahoehoe flow is present. So that shows you that at the same exact location, like right here, for example, you can have both Pahoehoe and Aa flows, And that might be a function of the temperature of the lava that's erupting at the time. There might be a slightly higher or lower gas content. Because the source is the same, the silica content is likely the same for these two particular lava flows. So it's likely variability either in most likely in temperature, but also gas content as well. So here is another. What do you think this is? What do you think? What do you think? It's probably a Pahoehoe flow, right? You can see the fluid structure of this lava flow as well. So temperature can change, certainly for lava flows, but it turns out that composition of magma can change over time as well too. So this is usually a point in my face-to-face classes where I hand out candy, and I'm sorry that I cannot virtually hand you a bag of M&Ms, but that's usually what I do. And the students open up the candy. They're not allowed to eat it right away. I tell them to imagine that every color M&M that you see in this picture represents one of the different 8 elements that are common in the Earth's crust. And we say, okay, so, and they look around at each other's piles of candy on their desks, and I say, so do you all have the same composition? And they don't. Every bag of M&Ms is a little bit different because they're kind of randomly assembled. I'm like, okay, so if you all have different compositions, what are ways that you could change the composition of your individual magma chamber? And we talk about it for a few minutes, and usually within a couple minutes, someone says, well, I could eat all my blue ones. Like, yes, you could. You could eat all your blue ones, and that would change the composition of the colors in front of you. And then someone will say, well, the person next to me, she and I we could put our magma chambers together and we would have a different composition overall. And yes, you would. You could add them together. You could also steal some from your friend and add some into your magma chamber. Maybe you grab all the red ones. And so then the composition, the elements that make up your magma chamber would also change. And so those are the 3 ways that the compositions, the minerals that are going to make up magma chambers, that's the 3 ways they can change. You can add things in, you can take things out. You can take things out by eating them, or any other function. You could drop them on the floor. Or you could mix them together. And those are the 3 ways the composition of magma will change. You can add stuff in, you can take stuff out, or you can mix stuff together. And that is your next activity in this class. All right, so enjoy.